The next topic is memory management. This is the very important task in our system, in our devices, in our gadgets which we are using in day-to-day life. Memory is very much required by us for storing, for retrieving, for accessing multiple kind of data in our system, in our devices. In this, we cover the overswapping, swapping, overlays, logical memory space, physical memory space, and contiguous allocation methods. In this, we discuss about the paging, segmentations, and so on. Now start from the management of memory, and memory management is the functionality of an operating system which handles or manages primary memory. Memory management keeps track of each and every memory location, either it is allocated to some process or it is free. It checks how much memory is to be allocated to processes and it decides which process will get memory at what time. It tracks whenever some memory gets freed and allocated and which one is unallocated, and correspondingly it updates the status. Memory management provides protection by using two registers, a base register and a limit register. Base register holds the smallest legal physical memory address and the limit register specify the size of the range. For example, if the base register holds 3 lakh and the limit register is 1,20,000 and something about to related this, then the program can legally access all addresses from the given range. In memory management, we have the number of processes to accessing that data, we have number of tasks for calculating the memory space and number of allocated processes tasks. We have to calculate how much space is remaining for allocation and how much space we have for allocation and how much space is already allocated and how much space is going to be released in how much time. Memory management provide protection. Have two kind of register which I told you just. In this, base register represent the minimum value and the limit register represent the maximum value and represent the how much space we can store into the system. Next topic is overlays and swapping. Overlay means replacement of a block of stored instruction or data with another. Overlaying is a programming method that allows programs to be larger than the computer's main memory. Overlay gives the program a way to extend limited main storage or provide a way to store the much more data as compared to the existing available space. A program based on overlay scheme mainly consists of following a root piece which is always memory resident, second set of overlays. Limitation of overlays is require careful and time consuming planning. In this, we have to define how much time is required for accessing and storing the data and how much memory we have for allocation for further processes. Programmer is responsible for organizing overlay structure of program with the help of file structures and also to ensure that piece of code is already loaded when it is called. Operating system provide the facility to load files into overlay region. Now The example of overlay, suppose total memory available is 140 kilobytes. Consider a program with 4 subroutines named read, function 1, function 2 and display. First, read is invoked that reads a set of data based on this data set value conditionally either of routine, function 1 or function 2 is called, and then display is called to output results. Here function 1 and function 2 are mutually exclusive and are not required simultaneously in memory. These number of functions help us for managing the memory and for storing, accessing this kind of information related to memory, how much space we have and how much space we can allocate and how much is required. Without the overlay, it requires 180K of memory, and with the overlay support, memory requirement is 130K. Without overlay, we have the number of functions for storing the data, like from base is 20K and upper is 40K. The function 1 overlay here 50K, and the function 2 is also overlay in the same, which is required the 70K. We can allow them to access in the memory by providing the overlay support into the system. Now the next topic is swapping. Swapping is a mechanism in which a process can be swapped temporarily out of main memory to backing store. Swapping and then brought back into memory for continued execution. Swap out allow to data exiting from the backing store, and swap in is a process in which we storing some data into the memory. Backing store is usually a hard disk drive or any other secondary storage which fast in access and large enough to accommodate copies of all memory images for all users. It must be capable of providing direct access to these memory images. Now in the swapping, a major time consuming part of swapping is transfer time. Total transfer time is directly proportional to the amount of memory swapped out and swapped in. Let's assume that the user process is of size 100 kilobyte and the backing store is a standard hard disk with transfer rate of 1 MB per second. The actual transfer of the 100K process to or from memory will take 100 kilobyte divided by 1000 kilobyte per second. It is the ratio is 1:10 seconds, and you can say 100 milliseconds. This is the diagram which is representing swap out and swap in. Operating system have the space for the users, and we can store the data in user space by swapping, and we can swap out from user space to backing store. This is the store, or you can say physical storage of data. If we are reading or we are picking some data from backing store to main memory, that is called swap in. If we are storing some data from main memory to backing store or physical memory, that is called swap out. Swap in and swap out are the processes where we are picking some data and we are storing some data from backing store. These processes we can represent on the basis of main memory and permanent storage, or you can say a backing store. Now the next is benefit of swapping. Allow higher degree of multi-programming allows dynamic relocation. If address binding at execution time is being used, we can swap in different locations, in different positions, in different situations, else in case of compile and load time bindings. Processes have to be moved to same locations only. Better memory utilization. And the next is less wastage of CPU time on compaction. And the next one is can easily be applied on priority based scheduling algorithm to improve the performance. Next topic is logical versus physical address space. Logical address space is a space which is allocated on logical basis, or you can say by CPU, or that is a kind of space where you can process your task, and the physical space is the permanent storage of data, which is you can say a backing store or the physical address space. Logical and physical address space. An address generated by the CPU is a logical address, whereas address actually available on memory unit is a physical address. Logical address is also known as a virtual address. Virtual and physical address are the same in compile time and load time address binding schemes. Virtual and physical address differ in execution time address binding scheme. And the next is the set of all logical addresses generated by a program is referred to as a logical address space, and the addresses which are generated by logical addresses and which are generated by the CPU and other devices is a logical address. The set of all physical addresses corresponding to these logical address is referred to as a physical address space. Logical address space is also known as virtual address, and physical address space is a permanent storage and stored in the disk files. Logical and physical address space. The runtime mapping from virtual to physical address is done by the memory management unit, you can say MMU, which is a hardware device. MMU uses following mechanism to convert virtual address to physical address. The value in the base register is added to every address generated by a user, process which is treated as offset. You can say offset is a kind of index which refer or which link to the storage space at the time it's sent to memory. For example, if the base register value is 10,000, then an attempt by the user to use address location 100 will be dynamically reallocated to location 10,100. The user program deals with virtual addresses, it never sees the real physical address. The next topic is single process monitor, monoprogramming. In the simplest case of single user system, everything was easy, as at a time there was just one process in memory and no address translation was done by the operating system dynamically during execution. This is the way, and this is the situation when a single task inside the system for execution and which is dynamically allocated by operating system. Protection of operating system or part of it can be achieved by keeping it in ROM. We can also have separate operating system or operating system address space only accessible in supervisor mode. The next topic is contiguous allocation method. So there is a kind of confusion in students. What is the continuous and contiguous? Continuous is a sequence or is a continuous statement where we know only the initial condition, We know where is the starting point, but don't know about the ending point of the allocation. In contiguous allocation method, we know the sequence is continue between the two endpoints from initial stage to ending stage, from beginning to end. We know from where the memory allocation is started and where to end. This is the chart which represents the contiguous allocation and non-contiguous allocation in memory allocation. We have the partition and two blocks, contiguous allocation and non-contiguous allocation. Contiguous allocation have single partition system and multiple partition system. It is further divided into two parts, fixed size partition and variable size partition. Variable size partition represent the dynamic or runtime allocation, and fixed partition is a static or fixed allocation. Have two types, equal sized and unequal sized inside the fixed size partitions. Now the next topic is partitioned memory allocation. The concept of multiprogramming emphasizes on maximizing CPU utilization. Utilization represents the maximum utilization of resources by overlapping CPU and input-output. Memory may be allocated as single large partition for processes to use or multiple partition with a single process using a single partition. Single partition system. This is the approach of operating system in the lower part of the memory and other user process in the upper part. With this scheme, operating system can be protected from updating in user processes. User processes or the other processes are not able to update the processes because it is a single operating system and handled by a single in a scheme, and single user operate the number of tasks on this system. Relocation register scheme known as dynamic relocation is useful for this purpose. It only protect user processes but also from changing operating system code and data. Two registers are used. Relocation register contains value of the smallest physical address, or you can say base address, and limit register contain logical address range, or you can say the upper address range. By this ranges and by this slots we can identify how much space we have, how much space is allocated and how much space is remaining for the further allocations. Both these are set by operating system when the job start, when the execution start. The next topic is memory management unit. This unit manages the memory and controlling the allocation of data between the range and between the available memory space. Hardware device that maps virtual to physical address. In memory management unit scheme, the value in the relocation register is added to every address generated by a user process at the time it's sent to a memory. The user program deals with logical address, it never sees the real physical addresses. In this diagram, there is a CPU which allocates logical address, like this is the 346, and the relocation register having the index value is 14,000, that must be added both of them and then allocate a physical address, that is the 14,346 into the memory. Dynamic relocation using a relocation register, and we can allow the number of process and only that memory which we have to available for allocation of number of resources. A pair of base and limit register define the logical address space which is available and which can be allocated, that is added to the physical memory offset index number to allocation of the particular memory space. This is the diagram which represents the base and limit register. Base and limit register define the logical address space like this. Limit register have this value and the base is this value. These range which can be allocated to the processes. Next is how to protect processes. Relocation register used to protect user processes from each other and from changing operating system code and data. We have some points for this, like first, base register contains value of smallest physical address, and the next is limit register contains range of logical addresses, and the next is memory management unit maps logical address dynamically. This diagram representing the way of allocation logical address space and how it matched with the physical and relocation register and what is the actual physical address inside the memory. CPU allocate the logical address and it will mapped with the limit register. If we have the logical address inside the limits, then we can allow it to access in the relocation register. Then physical address is added into this and we have the actual physical address inside the memory, and that is the address is the data address of memory. In this we have the next topic is multi-partition. In this we have the fixed partition in which we can store the data. Like there is multiple input queue, we have the partition number of, we can store that partitions by inputting some data inside them. Single input queue is maintained for storing the data for all multiple partitions in this which we are looking, and the separate input queue for each partition represent the A block and the single input queue representing the B block. In separate input queue, there is the parallel inputs to multiple blocks. In single input queue, there is a single queue for every block. Every queue get the value and passing the value from this way to the number of partitions. Multi-partition dynamic partitions. Main memory usually into two partitions. First, resident operating system usually held in low memory with interrupt vector, and the second is user processes held in high memory. Multiple partition allocation have the number of blocks, block of available memory, holes of various size are scattered throughout the memory. Scattered means the memory in holes in a distributed manner. When a process arrives, it is allocated memory from a large enough hole. Operating system maintain information about allocation, about partition, about free partition, about free holes, and about how much memory is allocated and how much memory is still we have for further allocation to the number of processes. Now, dynamic storage allocation problem are the following. First, how to satisfy a request of size of n from a list of free holes. Suppose we have the number of options for allocation of memory like first fit. In first fit case, we have to store the data in a particular location where the data can be entered. We do not have to care how much memory space is wasted and how much utilization is there. In the best fit, we have to take care of everything. We do not have to store the data in that location where memory space is wasted and where the memory is not properly utilized. The next one is worst fit. We can say worst fit is a kind of allocation method. In this, we are looking for the largest enough memory for storing the data. In this, we are not going to care for about first fit, about how much space is wasting and where it is located. Allocate the largest whole, must also search entire list, produces the largest leftover whole. Stats first fit and best fit better than worst fit in terms of speed and storage utilization. Next is fragmentation. For n allocated blocks, another n by 2 wasted due to fragmentation. Next topic is fragmentation. There is the two types of fragmentation: external fragmentation and internal fragmentation. Total memory space exists to satisfy a request, but it is not contiguous. In internal fragmentation, allocated memory may be slightly larger than requested memory. This size difference is memory internal to a partition but not being used. Reduce external fragmentation by compaction. Shuffle memory content to place all free memory together in one large block. The next point, compaction is possible only if relocation is dynamic and is done at execution time. In that case, we have some input-output problem, that is the latch job in memory while it is involved in input-output. Do input-output. The next topic is paging. As its name implies, partition of memory into small equal size, or we can say into chunks, and divide each process into the same size of chunks. The chunks of process are called pages and chunks of memory are called frames. So remember this thing, chunks of processes are called pages, chunks of memory are called frames. Operating system maintains a page table for each process, and every process have some location, have some memory address, and have the entry into the offset within the page. Every page tracked and every page information is stored into the memory as their information about the content, about the offset, about the location, about the page number, about the frame. So lots of information is stored into this about the pages, about the data. So this is the diagram which representing number of pages. Like we have the pages, page 0 to page 4. This is the logical memory. Inside this we have the number of frame number in which the number of data is stored. This represents the page table, and in frame we have the number of pages. We can say this is the physical memory and physical storage of data. Now the next is page allocation. In variable size partition of memory, every time when a process of size n is to be loaded, it is important to know the best location from the list of available free holes. In this we have to find the best suitable memory for storing the data in the available ones. This dynamic storage allocation is necessary to increase efficiency and throughput of the system. Most commonly used strategies to make such selections which are follows: best fit policy, in which we are looking for the tightly memory for our data, in which very less memory is going to be waste, or in which very less memory is going to be spacious. The first fit policy, allocating the first available hole which is big enough to accommodate the new process. And the next one is worst fit policy. In this method, allocating the largest hole that will leave maximum amount of unused space. Leftover space is maximum after allocation of that memory to particular data.